Here's a philosophical question. How can you see something that's clear? It's easy to see something that's green, right? It stands out in front of the background. It's green on top of something else that you would expect to be there. But how about something that's clear, like these clear glass rods? How come you can see them? They don't have any color. They let through the light from the background. So why do you even know that they're there? Well, you can see that there's stripes here in the background, and the clear glass rods distort those stripes. But why? Why do they distort? Well, when the light rays bounce off the background, they go in straight lines, but when they hit the glass rods, those light rays get bent, and so they don't go straight anymore. And so that changes the angles that the light rays hit your eyes. So it's the air to glass, glass to air that causes the light rays to change. However, what if there were a material that was the same as the glass, not glass itself, but had the same optical properties as glass? What do you think would happen then if light was going from this same optical property to glass and then back to that same optical property again? That's what this exhibit is set up to demonstrate. And let's give that a try. Let's see what happens there. But I want you to spend a moment and think. Make a prediction. What do you think will happen? Let's give it a go. Wow, the glass rods are now invisible inside of the oil. And the reason for that is that when the light goes from the oil to the glass rod, that's the same index of refraction. And index of refraction is sort of a measure about how much light bends when it goes from one to another. That is, the bigger the difference in index of refraction, the more the light bends. But this oil has the same index of refraction as the glass does, and so the light doesn't bend when it goes from the oil to the glass, so it doesn't change the background, it doesn't distort anything, and so the glass rods are invisible. Although you might notice that one of the glass rods is still visible. That's because that glass rod has a slightly different index of refraction than the other glass rods, and so since it isn't the same as the oil, you can still see it. It still distorts the background. All right, now I want to show you this other one over here. There's a lens, and you can see it looking against the background, and again, it distorts the image. It changes the image. Lenses are designed so that they distort the image in a very particular way so that we can either make things larger or make images with them. And they still also work because the light, when it goes from the air to the glass and into the air again, it bends the light rays. When we put it into the liquid, though, you'll notice that it doesn't bend the light anymore because it's the same index of refraction, and because it doesn't bend the light, it doesn't even look like there's a lens there anymore. You can't see anything. And if you've ever opened your eyes underwater when you've been trying to swim, you've had that same thing happen to you. It's often very hard to focus when you're opening your eyes underwater because the water and the cornea of your eye have almost the same index of refraction, so the light doesn't bend very much, so your cornea of your eye can't do its work to make an image on the back of your eye. If you want to see this in your house, you can just take an ice cube, find a clear piece of ice, and pull it under the water as well, and you'll see that the ice almost completely vanishes under the water. The same thing's true with, say, clear Jell-O. If you pull it underwater, you'll see that it's very hard to see because clear Jell-O and water have almost the same index of refraction, and ice and water have almost the same index of refraction. There is another interesting application of this technology. Imagine you're a jeweler and someone comes and brings you a ring that's got a green stone in it, and they tell you it's an emerald. Well, cubic zirconium can be dyed almost any color you want, and it can be dyed green just like an emerald, and so they will look the same to you. So if you're a jeweler and you don't want to take the gem out of the setting, is there any way for you to be able to tell that it's an emerald and not cubic zirconium? And the answer is there is. They sell liquids that are the same index of refraction as emeralds are. And so if you dip an emerald in that liquid, the emerald vanishes. But green cubic zirconium that's trying to be an emerald, if you put that in the solution, it doesn't vanish, so you can tell the difference. this does allow the jeweler to do something else, which is a little less okay. They can take a stone that has a small crack in it, that's a flaw in the stone, and soak that stone in that same liquid, and so the oil will fill in the flaw. And so then the flaw, which would normally be visible in a magnifying glass, will then become invisible when the flaw is filled with the oil. We have an activity online, we call them snacks, about looking at glass and vegetable oil to experience the changes of index of refraction. You can try all sorts of other things, like putting your glasses underwater if you have some, or try magnifying glasses underwater. In any case, there are lots of ways to play with indexes of refraction, and you should go ahead and give it a try and tell us what happens. Thanks.